In the last video, we proved proposition 1.3. That said, that if x and y are in a sigma relationship, then x and z are in a sigma relationship if and only if y and z are the same numeral type. In exercise 1.1, we're going to prove the same exact thing except for y instead of x. Now remember, I suggested that you try first and then check out the video to see how you did. So here's what we're going to prove in the first place. If x and y are in that sigma relationship again, then it is the case that sigma zy, that z and y are in the sigma relationship if and only if x and z are the same numeral type. In other words, what we're showing is that when x and y are in that sigma relationship, then y can and must be in that same sigma relationship with only and all numerals that are the same as x's type, as x's numeral type. The strategy we're going to have is we're going to start off assuming that sigma xy, and then we're going to show that the rest of it follows from there. And in order to prove the rest of it, we're going to say, we're going to have to do a two-pronged attack. We're going to assume sigma zy, assume that z and y are in this sigma relationship, and then show that it follows that x and z must be the same numeral type. And then we'll assume that x and z are the same numeral type, and we'll show that it follows that z and y must be in that sigma relationship. And that will prove both directions of the arrow. And then we'll have shown that if x and y are in that sigma relationship, then sigma zy if and only if tau of x equals tau of z. All right, so again, we're going to start off by assuming sigma xy. And what sigma xy means, the definition that we gave for this, is just that there is some numeral token of the same type as x, and you added 1 to that numeral token, and a numeral token of the same type as y is the result of it. So here's what it looks like. We're just going to name these random numeral tokens, x prime and y prime. And the primes don't really mean anything special. It's just another way to symbolize, another variable, right? So we said that by this definition, there must be some numeral token as the same type as x, and we said that was x prime. Another numeral token as the same type as y, and we said that was y prime. And these two numeral tokens are in that upsilon relationship. In other words, y prime is the result of physically adding one tally mark to numeral token x prime. Now, we're going to start off on the first leg of our proof, right? Proving that if z and y are in that sigma relationship, it must be the case that x and z are the same type of numeral. So we're assuming sigma zy, that z is in that sigma relationship with y. And again, by our definition over here, 1.3, right, we have a list of some criteria that must happen if it's going to be in that sigma relationship. Now this is very confusing because we have, z's and y's over here and x's on the left-hand side where I'm going through my proof. And then over on the definition side, we have x's and y's and stuff, and they're going to stand for different things, and that's very confusing. So I did these color-coded boxes hoping that you would see like the slots that these things fill. So the sigma zy, obviously y fills the same slot in both cases, but z is in that x slot, right? So try to keep this straight. I know it's really hard to keep it straight, but if you need to pause the video and line them up so that you know which one is going where, that would be very helpful. Then feel free to do so. All right, so if sigma is in that zy relationship, that must mean that there are two other numeral tokens out there. We'll call them z prime and y double prime, such that z is the same type as z prime, y is the same type as y double prime, and z prime and y double prime are in that upsilon relationship. Again, y double prime is the result of adding one tally mark physically to the z prime numeral token. All right, so that's what we've got so far. We've assumed sigma zy. What can we get from that? Remember, what we're trying to show is tau x equals tau z. We're trying to show that if sigma zy, then x and z must be in that the same numeral types. Well, up here we see that y equals y prime, right? And then we see that y also equals y double prime in 4, So it must be the case that y prime is the same type as y double prime. Now, remember proposition 1.2. Here's where things start to get really confusing with these different variables. All right. Proposition 1.2 said if you have an upsilon relationship between two numeral tokens, and we do have an upsilon relationship between these two tokens, x prime and y prime, and you have an upsilon relationship between two other tokens, and we do between z prime and y double prime, then if the first two numeral tokens in those two upsilon relationships are the same, then the other two must be the same. And we do have that. Notice, and vice versa, right? If and only if. So if the second two are the same, then the first two must be the same as well. And that's what we have in these two upsilon relationships, right? We have y prime and y double prime, and they are the same numeral type, right? So it must be the case that x prime and z prime are the same numeral type. Now we have x is the same as x prime, right? And down here in 6 we have x prime. And z is the same as z prime, and down here in 6 we have z prime as well. We said x prime and z prime are the same. Well, that must mean that x and z are the same. They are the same numeral type, right? Well, but think about that. That means we assumed that sigma zy, and we showed that it must be the case that x and z are the same numeral type. Oh, that's exactly what we wanted, right? Sick. If sigma zy, then tau of x equals tau of z. All right, now we're going to try to prove the other way, that the arrow goes the other way. If we assume that x and z are the same numeral type, then it must be the case that sigma zy, that's right, that z and y are in that sigma relationship. All right, so we'll assume that x and z are the same numeral type. Now, up here we said that x is the same numeral type as x prime, and down here we said x is also the same numeral type as z. That must mean that x prime is the same numeral type as z. But if that's the case, we have x prime is the same type as z, y is the same type as y prime, and we have an upsilon relationship between x prime and y prime. Well, by definition 1.3, we've got that sigma relationship too, right? We have an upsilon relationship between x prime and y prime. Y is the same type as y prime. Z is the same type as x prime. So z and y must be in that sigma relationship, sigma zy. And again, that's exactly what we wanted. We wanted to show that if x and z are the same numeral type, it must be the case that z and y are in that sigma relationship. So we've proved both sides of the arrow. Let's go ahead and take the fruits of our labors. We've got the double arrow, right? 8 and 12 show that the arrow go both ways, so we write that down. And now look at number 1, we assumed that sigma xy, and then in 13 we've shown that sigma zy, if and only if tau of x equals tau of z. That means we've proved what we wanted to prove. Exercise 1.1 complete.